Okay, so hi everyone. Welcome to my channel. I'm starting a new series of videos where I'll be explaining small, very niche, but really fascinating mathematical concepts. And these aren't just about memorizing formulas. They're more about understanding how things really work. And if you're serious, if you're someone who really likes to dig into the why behind the math, this could be your vibe. So today we are going to talk about eigenvectors and eigenvalues. So it's a concept from linear algebra that reveals the hidden directions in which a transformation acts most simply. So by the end of the video, you will not just know how to calculate them. I'm pretty sure you already know how to. You'll see what they mean and even discover a neat connection to 3D rotation. So yeah, so here we're going to build the intuition here. So imagine, I'll take the example of this. Imagine there's a matrix, okay, and you feed a vector into it. So we'll try to imagine a matrix as some sort of a machine, and you feed a vector into it, and what you get in return, it outputs another vector, right? So what I mean to say is that uh, this new vector that it outputs, it points in a completely new direction, right? But sometimes there are special vectors or like directions that don't rotate when the matrix acts on them. They might stretch or shrink, but the direction stays exactly the same. What I'm trying to say is it's actually very simple, and I'm going to provide the intuition with it. So suppose this is a vector, this is another vector, and when we feed it to the machine or like the matrix, we the vector we get in return. Okay, so they might shrink, they might stretch, but the direction it stays exactly the same. Now I'm talking about special vectors who might shrink, might stretch, but the direction stays the same. So usually that's not the case with any normal vector, but these are the special kind of vectors, and we call them the eigenvectors. So here you can see that they look at these arrows, and you can see they don't. Now if I increase the span of this, it stays on the same line, right? Uh, what I'm trying to say is it is not changing its direction. But yeah, the magnitude is changing as you can see over here. The magnitude is definitely changing, but the direction stays the same. So this is what I mean by an eigenvector. Geometrically, eigenvectors are like the natural directions of the transformation, and everything else may twist or rotate, but along these directions, the transformation is simple, just stretching or compressing, stretching, compressing, stretching, compressing. So that's it. Now I'm going to make this very concrete, and I've taken a vector, an example here. So in this, we have 2 into 2 matrix, and so basically what this matrix means is if you put a vector along the x-axis, multiplying by this matrix, it doubles its length. So it stays on the x-axis only, right? So basically it stays on the x-axis, but the length gets multiplied twice. And same thing happens in the y-axis, but here it gets like the vector triples in length, but it points straight up. It triples in length, right? But it points straight up. So the x-axis is an eigenvector with an eigenvalue 2, and the y-axis is an eigenvector uh, with the eigenvalue 3. So now you get what eigenvalues actually mean. And in the context of eigenvectors, what I'm explaining right now, it makes perfect sense. It denotes the magnitude, right? Since I said that eigenvectors don't really change their directions, they just shrink and compress and expand, but the direction stays the same. So notice how they remain pure, but I mean, they don't rotate. Now that's the geometric intuition of eigenvectors. So they show the direction where the matrix acts in the simplest way. Now I'll talk about the algebraic equation part, right? So this, let's see how we describe this this entire thing, how we describe it algebraic. So this is the defining equation. This is called the defining equation. Now this basically means that when a matrix A acts on a vector V, okay, the result is just the same vector which is scaled by lambda. Lambda is the scalar quantity here. So we can rearrange this into this, right? I think there will be a zero over here. It's zero. So yeah, we can rearrange this into this, and okay. I think we need a V here as well. Now it makes complete sense. So for a non-zero vector V, for a non-zero vector V to exist, this equation only works if the determinant of this is zero, and this is called the characteristic equation. Now if we solve this, we basically get the eigenvalues. Once we know lambda, right? Once we know lambda, we can plug it back in to find the matching eigenvectors, right? Now you can take an example of this. I mean, I haven't really looked upon examples, but yeah, you'll find examples of this anywhere on the internet. But this is the main concept behind how everything works, right? So these eigenvalues correspond to the direction where transformation acts purely as scaling. Now let's go back to the visuals. Um, so what this tells us is that the eigenvectors are the true axis of transformation. Now, any vector along these axes just gets scaled. Everything else twists or may twist or rotate, right? So if you understand this, you're just not going to do algebra, but you're actually seeing the geometry of the matrix, right? So yeah, this is a really cool 3D representation. I mean, you can play with it if you want. You guys can see this. I found it from ChatGPT, so yeah, that's pretty nice. Suggested me a cool website, so yeah, this was actually a very cool website suggested by ChatGPT. So I really love that. If you guys want, I can just touch the link of this website to the description. But what I'm trying to say is, if you have a 3D, okay, now here's another important, interesting fact about this. So if you have a 3D rotation matrix, which gives you the axis of rotation, I mean, what I'm saying is, if you have a 3D rotation matrix and you find its eigenvectors, right? 3D rotation matrix, and you find its eigenvectors, and what you're actually finding are the vectors that stay on its own span. Span means this, like the straight line, this is the span. So if the vectors stay on their own span, that is the direction around which everything else rotates. So basically what you're finding is, if you're finding the axis of rotation, yeah, everything else rotates around this vector. So, so basically, eigenvectors aren't just abstract, but they can tell you real tangible things about how space rotates and stretches. So pretty neat, right? Here's something fun, yeah. You can definitely go to this website and you can interact with the eigenvectors in real time. You can drag around, change matrices, and watch their directions stay unchanged. Now, that's the beauty of linear algebra when you're not just memorizing the formulas, you're actually seeing what goes behind them. Because even I didn't have the intuition behind the eigenvector. I mean, I was able to solve the problems, uh, which comprises of eigenvectors, but I didn't really have the intuition for a very long time. But yeah, when I had the intuition later on, I just it's like I leveled up and I can see things behind the mathematical problem. So next time you hear eigenvalue or eigenvector, imagine a weird matrix machine doing its thing, and it stretches along certain directions, uh, keeping everything else around. You've just found this special directions as in the eigenvectors. Yeah, that's it for today. I mean, that's it for today's deep dive. If you enjoyed this intuitive visual approach, stick around. I'll be posting more, mostly from maths. I'll be posting mostly from linear algebra, discrete maths, predicate, logic, calculus, or usually I might just switch to computer science as well if I want to. So yeah, that's pretty nice. Uh, Yeah. See you later.